Hello everyone, so my name is Michaela and today we are going on a journey. We are diving deep down to the bottom of the ocean. We are traveling more than 1,000 meters below and we will find something that is actually coming from space. But before we start, let me introduce myself. So that is the world map. I'm sure everyone knows where we are, right? So this is Australia, and I'm from here. So are there any geographies, some experts? Do you know where I'm from? Yes? Europe is very good. Do you also know the country?
The country that the pointing at.
Yes, is.
Can't read it though.
Yeah, that's
Czech
the tricky part.
Republic.
Almost close.
Hello?
Yes, I am from Austria. That's very good.
What was Austria?
I went to school there, and during school I realized that I like chemistry very much and also physics, but actually chemistry a little bit more, so I studied chemistry.
Just have to click on your slide again.
Yeah. So this is me when I did my defense, and this is actually a day where you talk to a panel about your research. And my research was about uranium in uranium ores, but also about uranium and plutonium in the general environment. And what I found out is that both uranium and plutonium are coming from this. What is this?
Oh,
Yeah?
Boom, boom.
Boom, boom. What is this exactly?
Nuclear boom.
Yeah?
a nuclear bomb.
Exactly.
Not exactly that. There could be atoms,
Or hydro bomb.
Very
hydro,
good.
lead.
So atomic nuclear weapons.
Atomic
So
bomb.
with the uranium and plutonium, I couldn't then tell where this is coming from because there are several different atmospheric and nuclear localities. And has anyone an idea what I'm pointing here? What is this? Yeah?
I forgot the name, but it's something about like the atoms, like this atom table.
Yeah, that's pretty close. Any other ideas? Yeah. So that's actually the nuclide chart.
Nuclear chart.
And the reason why I'm showing this is not only because I think it's an awesome poster in my room.
Also, you were researching about uranium, plutonium.
Exactly, very good. But the other reason is also I'm talking about this through the whole talk. So, and before we start, we need to distinguish between an element and an isotope, because during my talk, I will talk a lot about isotopes. So what do we see here? How is this called? Yeah? Exactly. So each element has a certain spot, a certain position, and it tells us the chemical properties. And here we see the carbon atom. So what are the building blocks of an atom? Yes, there is one. Yeah.
Protons.
Yeah.
And electrons.
Yes, very good. So we have a carbon atom in the core called the nucleus. We have the protons and the neutrons. And in the outer shells, carbon has two shells. We have the electrons. So has anyone came across the term isotope? Yeah? Can you explain this? Yeah. So, and how do we distinguish this? You can, yeah. Exactly, very good. So each element has a certain number of isotopes. And For example, here we have carbon. Carbon has 6 protons. And this basically gives you also the position in the periodic table. Yeah? So carbon is here. And carbon 12 has 6 protons and 6 neutrons. Carbon 13, another isotope of carbon, has 6 protons but 7 neutrons. And carbon 14 has 6 protons and 8 neutrons. Yeah.
So 13 and 14, you just add one more neutron onto it.
Exactly. And this is how you define an isotope from an element. They just have the same proton number but different neutron numbers. And this brings me back to this nuclide chart. So basically, each row is an element, and in the row we have all the isotopes listed from this particular element. And this then leads to the question, how are elements made? So it all starts with a bang, with a big bang.
Yeah, like sometimes elements are made from when stars explode, like when a red supergiant explodes, it uses neon, carbon, silicon, oxygen, and iron.
That's very good. You are one step ahead of us because we're still at the Big Bang. And here we produce hydrogen, helium, and tiny bits of lithium. But then, as you said correctly, all the other elements are produced in stars, either during the lifetime of the star or when a star dies. What happens when a star dies? Again, we have.
I see it the big one, because there's 3 different types: small, medium, large.
Okay, very good. So when a star explodes, we are talking about a supernova. So half of the elements are produced by a so-called S process, and S stands for slow neutron capture. And one candidate, so this is happening in a supernova, and one candidate for this is iron 60. So iron 60 is one isotope from the whole, from the iron element. So we know this pretty well, but the other half of the elements are produced by this R process, and R stands for rapid neutron capture. So they need a massive amount of neutrons in a very short time to be produced. And yes,
When they collide, they all start to make heavier elements because the neutron stars like denser, like
Yeah, denser than red giant.
yeah, and then it will just then those elements spread around, and then when the solar system forms, some of it gets captured with gravity, and that's where how the elements come in.
that's correct. So a neutron star merger is basically when two stars are coming close to each other, then they start to spin, get closer and closer and closer, and then bang. And plutonium-244 is produced by our process, and we wonder if it is produced, how it is produced. So this is our research question. We understand iron 60 very well. We know that it is produced in a supernova, but we don't know how plutonium-244 is produced. So the question is it produced like iron 60? Do we have a constant flux, like from a supernova? Then we would expect a signal like this. Or is there no correlation? And this would then point to a neutron star merger. So this is what we want to find out. Okay, so let's go on the hunt for plutonium-244. And for this, we need to go to the sea, the deep bottom of the sea, and collect the iron manganese crust. These iron manganese crusts, they grow very, very slow. For a millimeter, they usually take 500,000 years.
It's very old.
That is very old, yes. So the main component, as this name already suggests, is iron, about 15%, and manganese, about 60%. So here. But because they are growing so slowly, they basically get everything what is deposited on Earth from outer space, but also from here. So basically, you find the whole periodic table in this crust, which makes the chemistry very difficult. So we got a crust. It looks like this. It's massive. We got it by deep sea mining. So basically, these are diggers on the ocean floor. It was collected about 1,500 meters below sea level, and it was from the Pacific Ocean. Okay, so now we have our sample. Let's walk to my workplace. So here we are right now, and then it's a short walk here. So this is where I work, and this is the building where we have our heavy ion accelerator facility. But before we start, we have to do a bit of chemistry. So we want to measure iron 60, which means we have to extract iron. And this is pretty simple because iron is already the main component. So what we're doing, if you have this giant crust in your head, we have to drill 1 millimeter after 1 millimeter because we want to have a profile. But we don't only want to have a concentration profile, we also would like to know pH. And this is where beryllium comes in. So we measure beryllium 10 to a stable beryllium. And then basically you can date each layer. And we measured that a millimeter is 0.5 million years old. So we get an age profile. And we found out that this crust covers the time from 0 to about 10 million years. The plutonium chemistry is not so simple. So we couldn't do these 1 millimeter layers. We decided to divide them into 3 layers, 0 to 3 millimeter, 3 to 10, and 10 to 20. So you have different weights and also different time periods. So what you have to keep in mind is I used to talk in atoms because I'm extracting atoms. And this is a trillion. So that is 10 to the power of 12. So that is a 1 with 24 zeros. So that's a pretty large number. But this is not all. So basically what you have to do is add a trillion plus a trillion times a trillion. You get 10 to the power of 24 atoms, which is still not the right value because I only calculated this in 200 grams of crust for iron and manganese, but there's many more. But the point is, can you see the 6 plutonium atoms in this sample? Can you spot them? Yeah? Can you see them?
Yeah.
It's really hard. Huh? So
I can spot the face red.
you did?
Yeah.
That's really good. So the point I want to make here is that we have a massive amount of sample and we want to extract only atoms. So this involves a lot of chemistry and this is only a shortcut. So basically you have your crust sample, you dissolve it in acid, you do a liquid-liquid extraction here to get rid of the iron. And then you also do a bit of column chemistry here. So there are many, many, many steps that from this huge sample, you get to your plutonium. This brings me to the measurement. So this is, you remember this tower, and this is where we have our accelerator. It's accelerator mass spectrometry. So this is the tower here, and here are the different detectors and magnets. So the thing is, that we measured iron here at ANU. So in this little cathode, it's pretty small. This is a paper clip. Is our iron sample.
Hey, excuse me. Hey. Excuse me, Mom. Reverse.
Just okay.
Well, just
Yeah.
go back to the start.
Oh no, I can't. But you could sit. No worries. So we have our iron in this little cathode here, and this goes into this room here. That's on the top of the tower. And basically, what happens is we have our iron, and it is bombarded with cesium. And what happens is that the iron ions, together with oxygen, are getting extracted. And then they go through a magnet, a mass filter, because we have iron 60 plus oxygen. So iron 60, oxygen 16, 60 plus 16 is
72
what? 16
plus
plus
16. Oh, I thought you said
plus
60
16.
plus 60.
is 76. So basically everything with the mass 76 is coming through here. Everything else is already extracted. And then it goes through the stripper here. So the job of the stripper is that up to this point, we have iron together like a body with oxygen, and the stripper strips them. So basically you have oxygen and now iron is alone and travels through here. And then we do another mass selection and another one. And at the end, we count our atoms here. So this is done at ANU. For plutonium-244, we had to go to Amsterdam because, I mean, our machine is work standing for iron 16. But when it comes to natural plutonium-244, unfortunately, we can't measure it here. But they have an outstanding machine. It's called the Vega machine. You can see it here, thanks. And the principle is the same. It's just a smaller one. So this one is 1 MV and ours is 14 MV. Okay, this brings me to the results. So about 15 years ago, they measured for the first time iron 60 in such a graph. And they were able to see a peak where they were saying this is coming from a supernova because everything else was around background. More than 15 years later, we measured it again. A long time has passed. We have a better accelerator. Also, the chemistry was optimized. And we had a better time resolution. So you see, we could confirm this peak here, but we could also see another one. So we see two supernova at around 2.5 million years, but also at around 6.5 million years. And then plutonium. So for plutonium, we looked at 3 different isotopic ratios. That is plutonium-240 over 239, and this is here, 241 to 239, and of course the most important one, 244 over 239. So what you see here, the blue indicates values we know from the literature, and they are coming from the atmospheric weapons tests. And the red one is actually the thing that we measured. So if we look at this ratio here, that's 240 over 239, basically across the whole crust, it is anthropogenic, it is man-made. It comes from the nuclear weapons test. When we look at this ratio here, 241 over 239, we see, okay, in the first one, we see an introduction, but we were not able to see it in the last one, in the bottom one. If you remember, the crust was divided into 3 layers. If we look at the last one, and that is the important one, it is clearly, our signal is clearly above the anthropogenic value. So it is clearly coming from another source, and in this case, from space. But the question was, do they correlate? Does iron-60 correlate with plutonium-244? So what you have to remember is that for iron-60, we did these 1 millimeter layers. We couldn't do this for plutonium because it was not clear if we could actually measure in such a fine time resolution. So here we have combined the first 2 layers and the last one. So it is a bit tricky to compare them, but we could say, okay, here we also see an elevated peak. But then when it comes to the correlation, where we are like, okay, the ratio should be the same over the whole crust, we don't actually see this, or it's not as clear as we were hoping it to be. So the outcome of this study is that, yes, we found iron-60 and plutonium-244 in the crust, and we know that both are coming from space. We know that iron-60 is coming from a supernova explosion, from 2 or more, within the last 10 million years. But we were not quite sure what the plutonium-244 is coming from. Is it really coming from only a supernova, or are there other events like the neutron star merger responsible for this signal? So as research goes, we have to do more. And at the moment, my PhD student is working on a graph which has far more finer time resolution, 2 millimeters. So it is better to compare it with the iron-60. So today, what I wanted to tell you is that if you have a research question, you have to follow it and think about what you need. So first we had to collect the samples. Then we had to do a lot of chemistry. And then of course, you measure your samples and you get all your data and you have to discuss and interpret them. And then you might find the answer, or maybe only half the answer. But this is, I guess, the joy of research, that there are always open questions where you can go further. So yeah, that was it. Thank you very much for your attention.